After watching this video lecture, students will be able to write correct Lewis structures for compounds that do not follow the octet rule.
Let's go ahead and let's look at a couple of examples in which the rules for creating Lewis structures are slightly altered because of the features of the atoms involved. So if we go ahead and we look at the molecule BF3, we're going to put this molecule together in the exact same way that we have with all of the others we've looked at so far. As we've done in the past, we add up our total number of valence electrons, which is a total of 24 electrons. Put the least electronegative element in the middle when we're creating our structure, following rule number 3. Put all the other elements around the outside, okay, so the remaining atoms. We bond each exterior atom to the central atom, okay, so we've used a total of 2, 4, 6 electrons, okay, so we're going to subtract out that 6 from our total valence, leaving us with 18. We then take these 18 and we distribute them to the exterior atom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, and we subtract out these 18 electrons that we use, and we have 0 electrons left over. So then our next step is to check the remaining electrons so that each surrounding atom has its octet. And if we go ahead and we look at it, we notice that each of these fluorines, they're all bonded the exact same way to the boron. Okay, so we have 2, 4, 6, 8 electrons. So each one of the fluorines have their octet. If we look at boron, it has 2, 4, 6 electrons. Okay, so we notice that there is not an octet of electrons around boron. So normally what that would cause us to do is to subtract out some electrons or remove some electrons and double bond our fluorine to our boron. Now, what we need to know, or what we need to remember, is that in step number 3 up here, both beryllium and boron are actually exceptions to the rules. So this double bonding is going to be an inappropriate activity, and what we're going to use is we're going to utilize our formal charge calculations to help us see why this is an inappropriate type of bonding. Okay, so we're going to proceed through this structure as normal, and then we will chat about it. So let's go ahead and let's calculate our formal charges. Remember that in this situation we have 2 equivalently bonded fluorines, and obviously this fluorine over here is bonded uniquely, so the calculations for the fluorines, we're going to have 2 separate ones. One for this set and one for this set. Okay, and obviously we're going to have a calculation for our boron. So let's go ahead and let's start out with the fluorine with the single bond. Okay, I'm just going to put a little line like that. Okay, fluorine has 7 valence electrons. We're going to then subtract out the number of unshared electrons. Each one of these fluorines has 2, 4, 6. So, but since we're looking at individual fluorines, it's not 12, it's only 2, 4, 6, because we're just looking at that specific fluorine. Excuse me. So the 6 goes here, and then half of the bonding electrons. So we know that our bonding electrons are here. There's a single bond. So we're going to have half of 2, because each bond has 2 electrons. Okay, so 7 minus 6 plus half of 2, that's going to give us 0. So the formal charge on each of these fluorines is 0. Okay, so far we're off to a good start. 0 values for our formal charges are good. As close to 0 as possible is what we want. Okay, so let's go ahead and let's do the same calculation for the fluorine with the double bond. Okay, all right, once again, 7 valence electrons. In this case, remember we borrowed 2 electrons here. That's our erasing. Okay, and we put them here. All right, so the reality of it is we have 2, 4 unshared valence electrons. So we have 4 here. Okay, and remember we created a bond, so we have 2, 4 bonding electrons or bonded electrons. So we're going to take half of that 4. All right, okay, so what this ends up giving us is positive 1, because 7 minus 4 plus half of 2 is going to be a positive 1. So the formal charge on this fluorine is positive 1. So I'm going to put that into brackets. Okay, so now our charges are a little bit weird, and we'll talk about why, but let's do our final calculation. Let's just do boron real quick. Okay, boron has 3 valence electrons. Okay, it has no unbonded electrons, and it has 8 bonding electrons as we have it drawn here. So in this case, 3 minus half of 8 is going to give us -1. So our formal charge on boron is -1. Okay, now our next step would normally be to add up all of our formal charges and make sure that they make sense with respect to the structure that we have. So 0 plus -1 plus +1, that gives us an overall charge of 0, which makes sense. However, we need to think about electronegativity and the properties and desires of the individual atoms within the structure to kind of ascertain if this is the correct structure or not. So how are we going to do that? So if we look at, say, fluorine in this case, fluorine is going to be the most electronegative element, meaning that it wants to pull electron density towards it. Electron density is negatively charged. So if electron density is being pulled towards something, are we going to end up with a partial positive charge in that structure? Okay, the answer to that is obviously no. Okay, so in the same way, boron, okay, it's definitely not as electronegative as fluorine. Okay, we know that. So it's not going to pull electron density towards itself, so it's not going to have a partial negative charge. So the reality of it is that boron's unique characteristics end up making it where the desire to double bond to exterior structures in order to gain its quote-unquote octet is not necessary. And this type of concept or this type of approach is true with both beryllium and boron. They're both happy with a insufficient or less than 8 octet. So the reality of it is the structure that we would actually be looking for will be a BF3 molecule with single bonds. So we can just look at this real quick, right? The structure would look just like this. Okay, so very simply, this. If we calculated our formal charges, remember we've already done them for structures, or excuse me, that for the fluorines that are bonded in this manner. Okay, so we're just going to put zeros as our formal charges out here for fluorine. Okay, and our boron molecule, or excuse me, our boron atom. Okay, in this case, 3 minus 0, because there's no unbonded electrons, plus half of 246. Okay, that's going to give us a formal charge of 0. Okay, so remember our formal charges, we want them closest to 0. In this case, this structure right here is the most acceptable. And these are just two of the exceptions that you must remember. Okay, so although this is the direction you want to go, remember the formal charges also have to make sense, not just overall for the molecule's overall charge, but also with respect to where the electron density would like to lie on the molecule. So let's go ahead and let's look at another type of exception to the octet rule. So let's go ahead and look at the molecule PCl5. Okay. Just like last time, or in other examples, we would calculate the number of valence electrons as our first step. Our total valence electrons in this case is 40 electrons. Okay, we'd follow our second step and put our least electronegative element in the middle. Okay, so phosphorus in this case. We'd surround the central atom with the 5 chlorine atoms. Okay, then we bond each one of those chlorines to the central atom. Okay, and once we've bonded those to the central atom, we're subsequently going to count up the number of electrons that we used. So 2, 4, 6, 8, 10. Okay, so we've used 10 valence electrons. We're going to subtract out those 10. Still leaves us with 30 electrons. Those 30 electrons now get distributed to the exterior atoms, just like we've done in the past. So 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, 6 and 5 is 30. So I've used up my 30 electrons. Okay, and I have no more electrons to distribute. Okay, so I need to follow step number 5 and check if every atom has their octet. Okay, so let's go ahead and let's look at the exterior atoms. So all of the chlorines, each one of these chlorines is bonded to this phosphorus in exactly the same way. So if I look at this chlorine atom, I have 2, 4, 6, 7, 8. So each one of these chlorine atoms is content. They're happy. Okay, now phosphorus, let's check this out. It has 2, 4, 6, 8, 10 valence electrons. Okay, and so normally we would say that phosphorus is not following the octet rule, right? Because 8 is not, or 10 is not 8. Okay, so however, what you need to understand is that if your central atom is in period 3 or below, okay, d orbitals are now accessible, okay, and because d orbitals are accessible, that means that these elements can have what's known as an expanded octet. They can mix d orbitals with their s's and p's and subsequently give you more bonding capabilities, so they can hold on to more electrons. Okay, and because of this, we get structures such as PCl5. Okay, so we would go through this molecule, we would still check our formal charges, which we're going to do here, just like we would any other situation. You just need to remember that if your element that's in your central atom is in group 3 or below, which phosphorus is, okay, you're definitely going to be able to have an expanded octet. So let's check our formal charges. Formal charges for the chlorines. All the chlorines are bonded the same. 7 electrons minus 6 unbonded electrons plus half of the single bond that it has. Okay, that gives us a formal charge of 0. Okay, so each one of these has a formal charge of 0. Okay, our formal charge for our phosphorus. Phosphorus. Phosphorus has what? 5 valence electrons. Okay, it has no unbonded electrons. It has 2, 4, 6, 8, 10 pairs that are being shared between it and the 5 chlorines. Okay, so 5 minus half of 10 is going to give you 0. So your formal charge here is 0. Notice I have a very good structure. All of my values are as close to 0 or 0 in this case. So the formal charge calculations seem like the structure is very good. And if I add up all the zeros, that gives me an overall charge of 0, which corresponds to PCl5. Now, in some cases, guys, you might not actually have more atoms bonding to the central atom. So in this specific case, notice I have 5 chlorines. So I'm immediately bonding and forcing that octet issue to be at the forefront. However, there may be times where you have only 4 atoms or 3 atoms, okay, and multiple bonds might be what facilitates the expanded octet. And basically the way that's going to work is you need to be checking your formal charges. You need to check if you have a central atom that's in group 3 or below, you can double and are capable of maybe double bonding. You want to do that double bonding and then check your formal charges. Remember, the closer to 0 your formal charges on the atoms overall, the better off that structure. So if you have a central atom that's in group 3 or below, you may have to draw a couple different structures, maybe double bond here or there to make sure that you get the optimal Lewis structure.